Hello friends, this is part 3 of first semester mechanics and properties of matter question paper solution, paper PHYC1 physics, Dibrugarh University 2024. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. Also hype the video. Okay, so now you see, before we start, let me tell you one more thing. If you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. That's my Insta ID. You can follow me on Insta. So now let's start. In the last video, we have already solved up to question number 3. Okay, and today I'm gonna answer question number 4A, 4B, and 4C. Okay, these 3 questions. So first questions, explain damp oscillation with its general solution and find the frequency of damp oscillation. I have already answered this question. I have already made a video on this topic. Link is in the description box. I have written 4A and link is given in the description box. And similarly, this one also, I have made another video on this topic as well. Okay, that is also given in the link. I have written 4A, or then I have attached the link with that. Okay, do check the description box. Okay, now you see question number B. What are uniformly rotating and non-uniformly rotating frame of reference? Okay, deduce the following operator. We have to deduce this operator. So here this is not X, this is actually cross. Okay, though it seems to be X, but it is actually cross. Okay, so now let me answer this question. So here is the answer to question number 4A. This is the definition of uniformly rotating frame. So a frame is said to be uniformly rotating if its angular velocity is constant. Okay, and otherwise it is non-uniformly rotating frame. So here is the definition. A rotating frame is said to be non-uniformly rotating if its angular velocity is not constant, that means changing with time. Okay, so these are the 2 definitions. Now let us deduce this operator. This operator here you can see. Okay, let me show you how to deduce this. Suppose we have 2 frames. This is one coordinate system X, Y, Z, and another frame is, suppose this is X dash, this is Y dash, this is Z dash, like this. Okay, and this frame is rotating with respect to this frame which is in red. Okay, that these black coordinates are rotating with respect to the reds. Okay, and we have a point P here. Okay, and with respect to this coordinate system which is drawn in red, if its position vector is, suppose r is equal to x I cap plus y j cap plus z k cap, and with respect to the rotating frame, its position vector is, suppose x dash I dash cap plus y dash z dash j dash cap and plus z dash k dash cap. Let me consider that way. Okay, so now let me write what I have considered here. So these are the 2 frames here. You see, this is the origin, you can say, and this is the position vector r vector of this point P. Okay, with respect to these 2 frames, this is the stationary frame which is at rest. Here you can see x, y, z. Let me make the coordinate axis darker. Okay, and the rotating axis be x dash, this is drawn in red, this is z dash, this is y dash, suppose. Okay, this is the rotating axis, rotating system. Okay, now you see the position vector r, this position vector r in terms of its components along the either set of axes can be expressed as r vector in this in the frame according to this frame of reference x, y and z coordinate system, we will get x I cap plus y j cap plus z k cap, right? And with respect to the rotating frame, okay, let me take this x dash I dash cap plus y dash z dash cap plus z dash k dash cap, okay, k dash cap. So this is in rotating frame with respect to the rotating frame. With angular velocity, suppose omega, okay. So now you see, let us consider an observer in the system as this. I have named this system which is at rest. This system is S and the rotating system is suppose as this. The rotating system, this red color system is suppose as this, and the stationary system is frame is taken as S, okay. Just give me a second. This point is P, okay, this point is P. So now you see an observer in the system as this situated at the origin at O, okay, will observe the time derivative of R. So what will be the time derivative of R for an observer in the system as this, okay, for an observer in S dash, the time derivative of R, this time derivative of R will be, time derivative of x dash I dash cap plus time derivative of y dash z dash cap plus time derivative of z dash k dash cap, right? But the time derivative of this R relative to the observer in the system S. Suppose we have an observer at O in the system S. So for the observer in the system S, this is the system S, and here we have an observer. For him, this as the system is rotating, right? As this system is rotating. So the point P, it must have velocity along x-axis, y-axis and z-axis, as well as the unit vectors of this S system are rotating with respect to this observer, right? So here what we're going to have for an observer, just give me a second, let me rearrange these things so that I can have enough space to write here, okay. So for an observer at the frame S, okay, just give me one more second, just okay, for an observer in S, the time for the observer in S, we will get, with respect to the observer in S, the frame S dash is rotating, so time derivative of this R vector will be given by time derivative of x dash I cap dash plus time derivative of y dash z dash cap plus time derivative of z dash with k dash, and also the unit vectors are rotating, right? also the unit vectors are rotating, so that's why so here you see this is nothing but velocity of the particle P, right, with respect to x, y and z axis. These three components give the velocity along x dash, y dash and z dash. And now you see, in addition to this, the frame s dash is rotating with respect to s. Now you see, these are the two frames, suppose. Now this is a point P, okay, it has a velocity, suppose, for an observer which is at s dash, and this point is moving with respect to this s dash, and for this observer its time derivative will be given by this, time derivative of position vector will be given by this, because for the observer at s dash, so s dash is not rotating, right? For the observer at s, which is at rest, this frame is rotating, s dash frame is rotating. So in that case we have to add three more terms here. Time derivative of I dash cap, okay, x dash, time derivative of I dash cap plus y dash, time derivative of z dash cap, and z dash, time derivative of k dash cap. Okay, so hope you have understood this. Now you see, we know that velocity is equal to omega cross r. We know these things, right? And velocity, velocity is nothing but is time derivative of r vector, right? Omega cross r. If you consider the x component, that is x dash I cap, okay, in that case you can write omega is equal to omega cross, here we can write I cross, if you consider the x component only, right? Okay, hope you have understood this. So now here you see, so that's why here you see this rotating frame, angular velocity of rotating frame is omega. So that's why we can write, let me write on the other side, that time derivative of I dash cap, time derivative of I dash cap, that's going to be equal to omega cross I cap, time derivative of let me do one thing. Let me copy this last step. And okay, so here is the last step. Okay, so now what we can do, just give me a second, let me rearrange these terms. Okay, okay, so here is the last step we have got. Now we can write that this time derivative of I cap with respect time derivative of I cap can be replaced by omega cross I dash cap, okay, not I cap, I dash cap. Okay, similarly this can be written as omega cross z dash cap, right? And this time derivative of k dash cap can be replaced by omega cross k cap, because I have already told you that v vector, this velocity, is omega cross r, right? Hope you have got this relation. So if you take the x component, okay, so x component, so then time derivative of x component of v is the V is nothing but the time derivative of r, right? We know this time derivative of r. If you take the if this r vector is suppose x dash I cap dash plus y dash z dash cap plus z dash k dash cap, then if you take the x component only, x dash component only, then you can write this way: time derivative of x dash I cap dash is equal to omega cross, instead of r we're going to take the I dash cap here. Okay, if you consider the unit vector only, you remove this x dash. Okay, if you consider the unit vector only, then here we need to put only I dash cap, right? So hope you have understood this. Okay, so now let me write here. So here what we can do, we can replace this by omega cross, we can replace it by omega cross r, sorry not r, I cap. Okay, I cap, I dash cap, and just give me a second, sorry. Similarly, we can replace the time derivative of z dash cap as well. Okay, and k dash cap also. Let me remove this time derivative of z dash cap by omega cross z dash cap, and let me remove this one by omega cross k dash cap. Okay, so hope you have understood this, what I have done. Okay. So now you see, sorry. Okay, so now let me write, since, or here we can write putting this time derivative of I dash cap is equal to omega cross I cap, I dash cap, and time derivative of this z dash cap is suppose, not suppose, it must be this. Okay, and this must be equal to omega cross k dash cap. Okay, so that's what we have done, right? Hope you have understood this. And also we can replace this part, by this let me write time derivative of r is time derivative of x dash I dash cap plus time derivative of y dash into z dash cap plus time derivative of z dash with k dash cap. Let me write this bracket here, just give me a second. So why? Because you see, since S dash is rotating, with angular velocity omega, so we can put this. Okay, hope you have understood this. So if we replace this by this, let me represent this one by this time derivative of r. So here I have written dash on d. Okay, so hope you have understood this for the rotating frame. Okay, so now you see this part can be written this way. Now let me write time derivative of r vector with respect to t here, plus omega is taken out, cross within bracket we're gonna have x dash I cap dash plus y dash z dash cap plus z dash k dash k, and this is nothing but r, right? Here you see this is nothing but r, this one. Okay, so we can replace this by r. So plus omega cross, this is nothing but r vector, right? So this is time derivative. Here you see time derivative of r vector with relative to the observer in S frame is given by this time derivative of the r in S dash plus omega cross r, right? So if we remove the r from both sides, then we can write. So let me copy this relation and let me take a new slide. Okay, here is the new slide. This is the last step we have got. So from this above equation, so it is clear that the operators this differential coefficient with respect to time t and this the differential coefficient d dash by dt can be related or are related by this relation. Omega cross, this is not x, this is cross. So this is what we need to obtain, right? This is what asked in the question. So now let's move on to the next question. So what is the next question? Next question is this: discuss the difference between the streamline and turbulent flow with proper diagram. Okay, so this is question number 4C. Let me answer this question as well. So here is the answer to, there are 2 pages. Okay, here is the answer to question number 4C. Okay, so let me explain what is streamline flow first. Suppose here you see these 3 particles. If you consider these 3 particles P, Q and R, okay, at these 3 points, okay, this is velocity is v1 here, you can see clearly. Here the velocity is v2, okay, and at the point R velocity is suppose v3, okay. So now you see, though we have seen 3 different velocities, okay, when the point at the position R was passing the point Q, so its velocity is now v3 is the velocity of the particle at R at the point R, but when it was passing Q, its velocity was v2. Similarly, when this particle at point P will pass Q, its velocity will be v2. In that case, that means all the 3 particles, while crossing the same point, their velocity becomes equal. That means they cross the same point with the same velocity, though they are different. They have different velocities at different positions. Okay, if they are traveling in a line, that is called a streamline, and the particles in the same line, while passing through a particular point, at that point, if they have the same velocity, then that kind of flow is called streamline flow. Suppose we have 3 points, 1, 2, 3. These 3 particles are traveling with v1, v2 and v3. Suppose they will pass these 3 point will these 3 particles will flow, you know, in the same direction, suppose. And here we have a point, suppose here we have a point. All these 3 particles will cross this point, okay. And while crossing this point, at this point, if these 3 velocities, the velocities of these 3 particles becomes equal, then you know that flow will be called streamlined flow, right? And otherwise it will be called turbulent flow. Take the screenshot of this, okay. Now let me give you the definition of turbulent flow. On the next page we have, this is the turbulent flow, okay, right? So hope you have understood this. Then remaining questions will be solved in the next video. So thank you for watching. See you in the next video. Bye bye.